Okay, now let's switch from talking about the equilibrium constant in terms of concentration to talking about it in terms of partial pressure. So I'm still using the forward rate equaling the backward rate, but I'm going to write it in terms of pressure. The concentration of a gas mixture is proportional to the partial pressure of that. So if we assume that we can use the ideal gas law to express the pressure, the concentration of a substance in gas state in terms of its partial pressure, I would see that the equilibrium constant can be expressed as the ratio of the partial pressures. So in this case, I would have Kp. I would do this very same thing. My Kp is going to be just written in terms of partial pressures. So partial pressure of C, notice that I get rid of my brackets, that's talking about concentration, molarity. And now I'm going to use the capital P, meaning partial pressure. Capital P, and then I'm going to use the subscript of what the substance is. And I'm still going to raise it to the coefficient of its whatever the substance is, the products. So this would be the partial pressure of the first product, C raised to the coefficient C, times the partial pressure of the second product, capital D, raised to the power of little d, its coefficient. And on the bottom, I would have the partial pressure of A raised to the A power, and the partial pressure of B raised to the B power. So very similar in the way we construct the equilibrium expression for Kp. Now, we would want to say, like, how can I use that in terms of the relationship between the concentration and the pressure to determine a way to calculate one from the other? So here's where we go back and we use the ideal gas law. I know that molarity is equal to the moles divided by the volume in liters. For ideal gases, I can use I can sort of say that, so pressure times volume equals N times R times T. So if I now rearrange this to find N over L, it turns out that the partial pressure is equal to the molarity, N divided by volume in liters. So the partial pressure is related to the molarity times RT. So now I could take that and say that my Kp is equal to Kc times RT raised to the change in delta N. So what we would have to now look at as I would have to write out the Kp and C, that I'd have a whole lot of raised to the power of, I'd have a whole lot of RT terms. I would have one RT term for every coefficient of products in the numerator, and one RT term for every reactant raised to its coefficient. So it turns out that this delta N just kind of combines all those RT terms into a single term. So delta N is, and you could derive this if you worked it out individually and plugged in this Kp, plugged in this partial pressure for each of your terms in Kc, you could see that delta N is equal to the number of moles of gaseous products minus the number of moles of gaseous reactants. And again, when we talk about the number of moles, it's really the number of coefficients. I'm going to add up all the coefficients of gas products. They have to be gas and they have to be products. Take that as my first number, and then add up all the coefficients of the moles of the reactants that are in gas state. And I subtract the products minus the reactants. That will get me delta N. And so if I knew Kc, and I know R, that's a constant, that'll be given to you. I know temperature has to be in Kelvin because we're talking about gases. So, and then I multiply it by that delta N. And again, this could be a negative or a positive delta N. That will get me, I will convert it over to Kp.